When something falls into a black hole, where does it go, and will it ever come back out again? According to Einstein's general relativity, those answers are simple. As soon as anything physical, matter, antimatter, radiation, etc., crosses over the event horizon, it's gone. It can add things like mass, electric charge, and angular momentum to the black hole, but little else. It goes swiftly towards and eventually into the central singularity and will never escape again. But our universe isn't governed by general relativity alone, but also by quantum physics. According to our best understanding of quantum reality, there's much more that needs to be considered. Not only are there other quantum properties inherent to the raw ingredients that go into making a black hole: baryon number, lepton number, color charge, spin, lepton family number, weak isospin and hypercharge, etc. But the fabric of spacetime itself, which contains the black hole, is quantum in nature. Because of those quantum properties, black holes do not remain static, but rather evaporate over time, emitting Hawking radiation, and perhaps even more, in the process. When black holes do evaporate, then what happens to the information that went into creating them? Is it conserved? Is it destroyed? Is it encoded in the outgoing radiation? And if so, how? These questions are at the heart of perhaps the greatest paradox of all, the black hole information paradox. Here's both what we know and what we still need to find out. When a physicist talks about information, they don't necessarily mean what we conventionally think of as information, a string of letters, numbers, symbols, or anything else that can be encoded with bits. Conventionally, this is often described as the number of yes/no questions that must be answered to fully specify the properties of your physical system. Although even that description has limitations. These are all certainly examples of information, but those examples don't encompass all the various types of information that exist. Information can also include signals that enforce causality, quantum states, like qubits instead of bits, for individual entities, entangled quantum states between multiple entities, or any measure of the physical quantity known as entropy. That last one is tricky, because entropy, an inherently thermodynamical quantity, is very often misunderstood. You'll often hear statements like, entropy is a measure of disorder, or entropy always increases for any system. And while those things are kind of true, it's possible to make very ordered high-entropy systems and to decrease a system's entropy through the input of an external energy source. As an alternative, consider this. What entropy actually measures is the number of possible arrangements of the fully quantum state of your system. Every quantum state, every particle interaction, every piece of matter and energy in the universe contributes to the total information of the cosmos. When we think about black holes and the information paradox, it's this broader, more intricate concept of information that we must consider. Imagine a book being burned. Every word, every sentence, every paragraph turns to ash. But does the information truly disappear? No. In principle, you could trace each particle of paper and ink, track where they went, and from the ash, soot, chemicals, and gases produced, reconstruct every character on every page. The same goes for a shattered glass or a scrambled egg. As long as the fundamental particles are preserved, the original information about the system is preserved as well. But with black holes, things get peculiar. In general relativity, black holes have no memory of the types of particles or their properties that form them. A black hole only retains mass, electric charge, and angular momentum. This conundrum puzzled physicist Jacob Bekenstein in the early 1970s. The particles forming a black hole have their own properties and entropy. According to the second law of thermodynamics, entropy in a closed system can never decrease. It can only increase or remain the same. In pure general relativity, black holes have zero entropy, which simply doesn't add up. From the perspective of an external observer, the quantum particles forming a black hole increase the surface area of its event horizon as the black hole grows. As mass increases, so does the surface area, and consequently, the entropy rises. Bekenstein proposed that the information encoded by infalling particles appears to be smeared out over the event horizon's surface, leading to a definition of entropy proportional to the event horizon's surface area. This is known as the Bekenstein-Hawking entropy, the entropy of a black hole. But there's more. This idea led to a groundbreaking concept in theoretical physics, the holographic principle. It suggests that all the information contained within a volume of space can be represented as a hologram, a two-dimensional surface that encodes the three-dimensional data. In the case of black holes, the event horizon acts as this surface, encoding all the information about the particles that have fallen into the black hole. Will that information get destroyed? This definition was very exciting, but the notion that we had made sense of the universe, of entropy, information, and black holes, was extremely short-lived. In 1974, just 2 years after Bekenstein's earliest work on the topic, Stephen Hawking came along and not only had a spectacular realization, but performed a tremendous calculation to go with it. His realization was that the standard way of performing quantum field theory calculations made an assumption that space would, on tiny quantum scales, be treated as though it were flat, unaffected by the general relativistic curvature of space. However, in the vicinity of a black hole, this wasn't just a bad approximation. It was a worse approximation than it would be under any other conditions that occurred within our physical universe. Instead, Hawking recognized the calculation needed to be done in a background of curved space, where the background spatial curvature was given by Einstein's equations and the properties of the black hole in question. Hawking calculated the simplest case, for a black hole with mass only, without electric charge or angular momentum, in 1974, and recognized that the state of the quantum vacuum, or empty space itself, was fundamentally different in curved space, near the black hole's event horizon, than the state of the quantum vacuum far away from the black hole, where space is flat. Hawking's calculations led to a groundbreaking discovery. Black holes aren't completely black. They emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon. This radiation implies that black holes can slowly lose mass and energy over time, eventually evaporating completely. But if a black hole evaporates, what happens to the information it has absorbed? Does it get destroyed, violating the principles of quantum mechanics? Or is there a way that this information is preserved? This question, known as the black hole information paradox, remains one of the biggest unsolved problems in theoretical physics. As physicists continued to grapple with the implications of Hawking radiation, a new, provocative idea emerged in 2012 that added another layer to the puzzle: the firewall hypothesis. This hypothesis suggests that the event horizon of a black hole might not be the smooth, featureless boundary that general relativity predicts. Instead, it could be a searing wall of energy that incinerates anything that crosses it. The notion of a firewall was proposed to resolve the apparent contradiction between quantum mechanics and general relativity. According to quantum mechanics, information cannot be destroyed, but if black holes evaporate entirely, what happens to the information they contain? The firewall hypothesis posits that information is not lost, but rather encoded in the high-energy particles at the event horizon. This idea sparked intense debate among physicists. Some argued that the firewall hypothesis could solve the information paradox by preserving information in a way that is consistent with quantum mechanics. Others pointed out that such a firewall would violate the equivalence principle of general relativity, which states that an observer falling into a black hole should not experience anything unusual at the event horizon. The truth is, despite many declarations over the years that the black hole information paradox has been resolved, nobody knows. Nobody knows whether the information is preserved, whether it's destroyed or erased, and whether it depends on what occurs in a black hole's interior, or whether it can be completely described from an outside observer's perspective. We have mathematical correspondences between what happens on the inside and the outside of a black hole, including an underappreciated fact that takes us beyond the semi-classical approximation used by Hawking, that when radiation comes out of a black hole, it should maintain a quantum mechanical entangled link to the black hole's interior. We have devised methods that allow us to map the entropy of a black hole's interior onto the outgoing radiation that arises due to the Hawking mechanism, which suggests, but does not prove, that we may be approaching a mechanism for understanding how the information that went into creating a black hole gets encoded back into the universe outside of the black hole's event horizon. Unfortunately, we don't know how to calculate individual bits of information using any of these methods. We only know how to calculate overall amounts of information as though we're putting them on a scale, seeing whether they balance or not. That's an important step, but it isn't enough to resolve this paradox. The solution to the black hole information paradox may come from an unexpected direction. Until next time, keep exploring the information because the journey has only just begun.